Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem valid anagram, and we're actually going to be solving this a few different ways, so maybe you will learn something today. So we're given two strings s and t, and we want to return true if t is an anagram of s, or basically if both of the strings are anagrams of each other, and false if they're not anagrams. So main thing that they don't mention in this problem is what exactly is an anagram. And basically, it means that, to call T an anagram of S is basically saying that using the characters of S, all of the characters, right, every single character, we can create the string T. So basically, they're made up of the exact same list of characters. So the string S, you can see that it has three A characters, one N character, one G character, one R character, and one M character. So it's made up of, in total, 7 characters. So that must mean that if T is an anagram of S, T has to have exactly 7 characters as well, which clearly it does have 7 characters, but are they the exact same characters as I wrote up above? Well, let's check. Okay, does it have 3 A characters? 1, 2, 3. Yep, it has 3 A characters. Does it have a single N character? Yep, it has exactly 1 N character. Does it have a G character? Yes, exactly 1 G character. Does it have an R? Exactly 1 R. It has exactly 1 M as well. So it has the exact same characters and the same quantity of each character. That's also important, right? Because 3 A's have to exist in T as well. So in this case, they're anagrams. We can return true. That's great. Second example, rat and car. Both of them have an R. Both of them have an A character, but one of them has a T while the other has a C character. They're both the same length. They're both length 3, but they have one differing character, so they're not anagrams. We return false in this case. So the first solution I wanted to talk about is probably the most obvious one, and probably by just listening to me talk about anagrams, you might be able to come up with this by yourself. We just want to count the occurrences of each character in both strings, right? What's the easiest way to do that? Well, you could use an array or a hash map. That's what I'm going to use. I like hash maps. Basically, what the hash map is going to look like. So basically, we're going to have 2 hash maps, one for each string, and the key value in the hash map is going to be the character. So for example, A in string S, right? Let's use a different color. So A in string S. So how many A's are there? There's 3 A's, right? The value is going to be the count. The key is just going to be the character. We're going to do that for every single character in the string. So that's A, N has 1, G has 1, R has 1, and M also has 1. And we know that T is the exact same, right? It has 3 A's, 1 N, etc., etc., right? I could continue this. So in the end, you can see that they're the exact same hash map, right? Once we've built these hash maps, we can then go through the keys and then compare that the counts for each character are the exact same, which in this case, yes, it is. So then after that comparison, then we know that they're anagrams, then we can return true. And how exactly I'm going to do that is I'm just going to actually iterate through the keys of one of these. So in this case, for example, I'm just going to iterate through all the keys in string S. So A, N, G, and then make sure the counts, right? We want to make sure that the count of each of the characters is the exact same. And if we make sure that both strings have the exact same length, before we actually do the hash map stuff, then we actually only have to iterate through one of the hash maps and comparing it to the other hash map, right? Because if we make sure that T has exactly 3 A's, T has exactly 1 N, T has exactly 1 G, etc., etc. If we make sure that all of that is true and that's inside of T, then we pretty much know T is exactly the same as S because they have to be if they are the same length. So that's the solution. Time complexity of this is big O of N, or rather, let's say big O of S plus T, because we're gonna have to iterate through both of the strings. So that's the time complexity. The memory complexity is the same, S plus T, because clearly we are building hash maps that are gonna be of size, potentially up to the size of S and the size of T. So the downside of this solution is we are gonna need some extra memory, and the second solution that I show you is actually gonna solve that memory problem. So stay tuned in the video if you want to see that. But for now, let's jump into the coding solution of this hash map solution that I'm talking about. Okay, so now let's code it up. And like I mentioned, Main thing we're just going to be doing is counting the characters in both of the strings. So we're going to create hash maps for that. This is how you can do that in Python. But remember, before we even do that, we want to make sure that the length of both strings is exactly the same, because if they're not the same length, then of course it's impossible for them to be palindromes. So we can immediately whoops, then we can immediately return false if they are not the same length. Otherwise, we can actually run the algorithm. So let's just go through the strings at the same time. So we can iterate basically through the length of the string s, because we know they're both the same length. So we can just use the index I for both of the strings. Count s is basically going to count the occurrence of each character in string s, of course. So each time we see a character, so a character is basically going to be s at index I. That's the key of the hash map. Every time we see a character, we want to increment the count of that character by 1. So can we just say 1 plus this? Can we just say 1 plus this? Well, in Python, no, because what if that character doesn't even exist in the hash map yet? Then this is going to throw a key error, right? Key does not exist. So to get around that in Python, at least, there's a nice little function with hash maps that you can use that's called get. So get this, this key, and it'll basically do exactly what's being done over here on the left side, but the second parameter to this function is basically a default value. So 0 is the default value in this case. That means that if this key does not exist in the hash map, then the default value that this function is going to return is 0, which is of course what we would want it to return, right? So with this line, we're just counting the occurrences of each character in string s. We can do the exact same thing with string t, just by copy pasting this and then changing everything to t. So making sure we use the t hash map and making sure we iterate through the string t, right? T at index I. So that's pretty much it for building the hash maps. Next, we want to iterate through the hash maps and make sure the counts are the same. So let's say for C, for the character in count S, so we just want to make sure the counts of both hash maps are the same. So count at character I is equal to count T at character I. So the counts are the same. Actually, in this case, we'd want to make sure that the counts are not the same, because if they're not the same, then we basically know to return false immediately, because then we know that they're not anagrams. If you have noticed, we're iterating through the keys in Python, at least. We're iterating through all the key values of count s, right? The count map of string s, and C is going to be the key. But what if that key does not exist in the t map, right? Count t. What if it doesn't exist in this map? Well, again, we can use that default function of get so that it doesn't throw a key error for us, and it'll return a default value of 0. So that's basically the entire algorithm, right? We built the hash map, we performed the check, and then if we never return false here, that must mean that they are anagrams. So then if the loop exits, we can go ahead and return true. That's the entire code. Let's run it to make sure that it works. So you can see on the left, it does run. It's relatively efficient, though it doesn't reflect that on Leetcode. But basically, you can actually do exactly what I just showed you with one line of code, at least in Python. But I think this is kind of cheating, and it probably won't work in an interview. But counter is a data structure in Python, which is a hash map, but it basically counts things automatically for you. So we can can run a counter on S, and we can run a counter on T, and if these counters are exactly equal, basically by doing the equal sign, I'm just doing what I did down here, right, with the for loop, but the equal sign does it for us instantly. So it does that, and then we can just return the result. If they're equal, it'll return true. If they're not equal, it'll return false. I can run that and make sure that it works, which it does, and it's actually slightly more efficient, I guess. The overall time complexity and space complexity of both of these solutions is exactly the same, just this takes more lines of code because we're actually explicitly writing out all the operations. So now what if, as a follow-up question, your interviewer asked you, how can you make a solution where we don't actually need extra memory? Can you do a solution with O of 1 memory? How would you solve that problem? It's a good question, and the solution is actually simpler than you might think. Just kind of thinking about how anagrams work, if you took all these characters and put them in a hash map where we can count the occurrences, then it's pretty easy to check if they're equal. But isn't there another way? What if we made sure that the characters show up in the exact same order every single time? What do we mean by order? Well, one possible way would be sorted order, right? Because if they really are the exact same characters, then if we put them in sorted order, then they should actually become the exact same string. Then we can literally just do an equals operation on both of the sorted strings and guarantee that they're going to be equal. But the downside is, what's the time complexity of doing sort? Well, in some cases, with bad sorting algorithms like bubble sort or something, it might be n squared, right? Good sorting algorithms can do it in n log n time, right? Worst case, big O of n log n time. But the space complexity is kind of iffy. Usually sorting algorithms, at least good ones, actually do use extra memory. They use O of n extra memory, but sometimes they don't. Sometimes they can be really optimized and actually run on constant memory,